Our first presenter is David Perillo of the European Space Agency, and he will be giving us a talk on using EDS for spacecraft avionics. Thanks, everybody, and enjoy the day. David.
Good morning. I am David Perillo from European Space Agency. In this presentation, I will provide a summary of the research activity conducted by European Space Agency together with some of the largest space companies in Europe to adopt electronic datasheet as a reference format for describing avionic units at different levels of detail. The study was promoted by SAVOIR working group, and it extends on the SOIS EDS standard from CCSDS working group, so as to cover multiple domains in a single electronic datasheet. The study is therefore part of an international standardization activity with other space agencies, mostly NASA, to create a common format for representing space domain knowledge. Marek Prochazka was the technical officer for this activity, whereas I supported the technical activities of this study. The agenda for this presentation begins with the context of the study to provide a general background and introduction to the topic. Then we will discuss the proof of concept prototyped along the study, and finally the conclusion we came to. The first topic of the presentation is the study context, and we begin by answering the question, what is an electronic datasheet? Electronic datasheet, EDS in short, is an electronically readable document which can replace all paper ICDs, interface control documents, of devices and units intended to be integrated into a spacecraft. Because of their digital nature, EDS files can be imported in the system reference database used by mission control system and electronic ground support equipment. EDS can also be exploited to generate human-readable documentation, to generate parts of the flight software handling and communicate with your device, as well as to test that a device conforms to it. It can really be a valuable artifact if you have the facilities to exploit and can be used along the entire mission lifecycle. As already mentioned, our study leverages the SOIS EDS standard from CCSDS working group. The SOIS EDS standard consists of a formalized language providing constructs to enclose communication and data handling information in an interchange format encoded as an XML file. The syntactic definition of the language is achieved by means of an XSD file, XML schema, delivered by the CCSDS working group together with the Blue Book and together with the dictionary of terms. The Blue Book defines both the what and the how of the language, because it not only provides the language specification but also implementation guidelines of specific modeling patterns as XML snippets. On the other hand, the dictionary of terms is a support document for the definition of the ontology. Even though SOIS EDS is intended to cover only communication and data handling information, in the context of this study, the study participants came to the conclusion that the standard is suitable also for describing multiple domains other than communication and data handling. This is how a SOIS EDS model looks like. At the top level, there is a datasheet which contains the description of the device and some additional information. This is then organized in packages defining components, interfaces, and data types. Component behavior is defined by state machines and activities. A state can execute activities as part of its entry or exit action. In turn, activities can send commands through the component interface. On the other hand, state transitions can be triggered by different kinds of events, such as timers or received commands. At the same level of component, there are data types and interface definitions. Interfaces are declared as a set of commands. Data types can be container fields, array of data types, or scalars limited by numerical ranges. The reference mechanism is implemented by referencing the qualified name of a model element as a string of characters. The drawback of this approach is that the user of the IADCS models must be particularly careful when changing names of an existing model element, or the risk is to mess up with the existing references to that model element. One of the outcomes of the activity was to build 4 proof of concept using EDS to represent existing devices or units. Each proof of concept is a big piece of XML file ranging from 6,000 to 10,000 lines of code. And in order to keep those EDS files consistent and valid, we relied on a tool called SECT, which is the acronym for SAVOIR EDS Common Tooling. SECT tool was developed by the British company CGI as part of this study. Basically, what the SECT tool can do is to decode SOIS EDS files, to validate them, and to generate simple artifacts such as HTML documents and headers. The tool was also useful to check that named reference to model elements were consistent and unique across the datasheet. Of what mentioned so far, these slides provides the correspondence between a paper ICD in the top right and the corresponding SOIS EDS XML model in the bottom left. Every device property in the ICD has a corresponding attribute in the XML extract below. When the digitalization process is fully implemented, the paper ICD should be automatically generated from the EDS models by means of an automatic model-to-text transformation. This means that the paper ICD becomes just a convenient representation of the model at a specific point in time. SOIS EDS standard was taken as the basis for this activity, and it was used to cover also multiple domains such as thermal properties of a device, covering everything is related to heat, mechanical properties of a device, for instance, weight and size, electrical domains, including power consumption and connector types. Communication and data handling was already covered by the SOIS EDS standard, and we used it as it is. Just a little bit of history. In the early stage of the study, we initially defined a brand new datasheet syntax covering multiple domains. However, around the half of the project, our study participants came to the conclusion that SOIS EDS was already adequate to cover multiple domains using the existing concept. For instance, the concept of interface could be used to enclose the physical properties of a device. Therefore, in this study, we benefit of the SOIS EDS standard and the dictionary of terms. And in return, as outcome of the study, we provided feedbacks and contributions to the CCSDS committees for the SOIS EDS standard. Next topic to discuss is the proof of concept section. This consists of multiple use cases and devices described as EDS models. Given the complexity of each device, I will only provide an overview of how we managed to enclose physical properties of a device within the SOIS EDS syntax. The ICD extract on these slides shows some attributes describing electrical properties of a device interface. Among other, we have the protection from electrostatic discharge, ESD, isolation, power mode and reference voltage, as well as short circuit tolerance and power consumption. Of course, to provide all this information, it takes a specialist in the matter, and that is where the collaboration among people with different specialties come into play. For instance, digging deeper in the model, tolerance levels to short circuit have been specified using numerical range types. Something more sophisticated was done for describing the power consumption values, which have been differentiated for different utilization states, idle, nominal, and peak. These three power consumption utilization states have been modeled as states in the component state machine, and then referenced in this interface declaration by their name. Same thing was done for the mechanical representation of the device, defining all meaningful mass properties that must be provided by the mechanical engineer when instantiating a mechanical view of a device. Once again, the numerical values of these properties can be expressed using range types. We arrived almost at the end of the presentation, and it's time to get to conclusions of what achieved and understood along the study. First positive conclusion is that we managed to enclose a significant amount of ICD information into a set of XML files structured according to the SOIS EDS schema. Along the study, since all study participants used quite intensively the SOIS EDS standard, the participants collected some non-blocking feedbacks for the CCSDS committee for inclusion in the next release of the pin sheet update of the Blue Book. Also, at the end of the study, it was clear the potential of deploying an EDS ecosystem as part of the mission lifecycle. These could contribute to produce savings of time and cost, as well as to mitigate risks such as the risk of having inconsistent or incomplete documentation. A major point of attention is that EDS files must be adequately verified before being accepted. To this end, the user expectation on the model quality should be part of the specification process. The syntactical validation of EDS models is straightforward, as it can leverage the good tapping system of the SOIS EDS standard. In our study, the SEC tool was helpful to verify conformance checking of prototyped models against the standard. Currently, space companies adopt different databases and electronic formats to enclose their domain-specific knowledge. Most of these formats are either company proprietary or are simply too specific for being easily reused widely across the space industry. However, most of the concepts used to describe a device have a very similar meaning in different formats. Therefore, one could think about creating a higher level standard or an ontology to enclose all concepts of interest for a datasheet, with the purpose to automatically map datasheet to alternate domain models. If such an ontology would be available, we could be in theory able to transform electronic datasheet from one domain model into another. Even though more research activity is still necessary to create such a higher level standard working as a space ontology reference, this could probably be a promising technology to investigate as a research topic in the near future. The activity for this study was run by the European Space Agency. The prime contractor was CGI, formerly SAVOIR, with subcontractors Airbus France from Toulouse, OHB Bremen, Germany, Thales Alenia Space, France, and RUAG Aerospace involved to create EDS models of their devices. Thank you for attending this presentation. I am available to take your questions, if any. Otherwise, you can also reach out myself and Marek at the email addresses in this slide.
All right, thanks a lot, David. We do have a question in the Q&A, and so we have about 10 minutes, so I'm going to encourage folks to go ahead and get a few more questions in the Q&A. First question is from John. did you take the step of creating C header and or source files from the XML for your flight software? If so, was it an existing tool or did you create your own?
Okay, can you hear me now? Because we had problems before with the audio. Is good the level of the microphone?
Sounds
Can you
good.
hear me well? Okay.
Yes.
So yes, we developed along the study. It was developed a tool called the Sector, SAVOIR EDS common tooling, which will be made available on the ESSR website of the European Space Agency. That is able to validate the code, the XML file with the SOIS EDS syntax, and to generate several different artifacts, such as the HTML documentation and the C header files. Actually, by now it was a study, a research activity. So we did the inverse process. We took C header files manually implemented in real flight software, and we managed to produce the code from XML files, somehow duplicating existing reference code used for implemented for the flight software. That was the question, right? So is the tool available? Yes. Is the SEC tool is able to generate the C header files? Yes. Those other files are used in real flight software. Actually, we leveraged existing header files, and we built, we implemented the code generator from existing flight software code. Did it answer the question? Or?
Excellent. We'll give that person a moment to follow up if there's any additional questions or clarifications. But in the meantime, we have 2 more questions that did come in.
I can also add other points. If I also have other things to add in the list. So if we have time, then I can go through my points. Otherwise, okay. I'm happy to answer the question.
All right. Looks like questions are streaming in now. So next question from Peter Fiddleman. How do you envision the EDS XML descriptions being created in the first place? By handwriting the XML, or are there tools that assist with it?
That is an excellent question, really. Thank you for asking, actually. So there are different ways. One could be, as suggested, to encode this XML by hand, which is, I think, awful activity. We had to do something like this in the beginning, and it's indeed not a pleasant activity, and also error-prone. A second would be to implement an authoring tool, which is something in our agenda, to create an authoring tool, at least to visualize, to edit the EDS files. But what the approach followed in the study, one of the approaches followed in the study was, and I think is a very valuable one, is to generate those EDS files out of existing databases, other databases. Because we have the information, sometimes the companies have their own modeling standards, which enclose a lot of information, way more than those that can be disclosed in a datasheet. So the EDS files can be used to represent information that should go in, let's say, a public ICD, and those XML files could be produced out of existing system databases using a model-to-text transformation, or model-to-model transformation. Did I answer the question, or is there system doubts?
Yeah, like the last one, we'll see if the person responds back with a follow-up question. But in the meantime, next question from Lee. Has any consideration been made on the relationship between this work and more general model-based systems engineering efforts? This work seems like it can play a part in MBSE.
Nice point. Really, all brilliant question. Like, there is a kind of controversy, I would say, because this can this activity, this study can indeed play a role in MBSE. But here we are enclosing only part in this data sheet. We enclose only part of the information, so it's more an exchange format that can be used to do automatic transformation and to generate code and to have a consistent information in represented with a formalized structure, semi-formal representation of the data. But it's from this EDS model, you cannot automatically, let's say, calculate other physical properties, like sum up the mass properties and create the entire mass of the system, or to recursively aggregate components so as to describe the system or the device at inner level. More, this is to describe externally how a device works, so the interfaces. That's why there is a kind of difference between this work and pure MBSE. This should be more an extract of from information held by an MBSE tool, or can be used to import, export information from to another more complete MBSE tool. I finished responding this question.
Okay, great. Next question is from Rand Willock. What tooling exists to verify system requirements based on EDS information?
To my knowledge, there is no tool that automatically verifies system requirements. We can somehow try to verify traceability. Not sure if automatically, but there is no comprehensive tool at MBSE level that can verify EDS information against specification. At least that is to my knowledge.
Okay. All right. Next question from Vito Fortunato. How is this related to CCSDS XTCE standard, and do they link each other in any way?
We didn't consider other standard from CCSDS working group. We focused mainly on SOIS EDS as a way to enclose information in a standard way. So instead of reinventing the wheel and creating a brand new way to encode data, we selected the EDS, SOIS EDS format, and we use this. There was no, at least at the current stage, no intention to leverage other standards.
Okay, great. Another question from Kevin. Now, what are the next steps in order to for more projects in ESA to adopt EDS? How do you get folks to adopt this?
That requires a vision. It's maybe not easy to answer this question in just a minute. We need to create an ecosystem around this. We are working hard to integrate EDS in other studies, so as to use the EDS as import-export format to create import-export facilities from EDS from two other MBSE tool, like Taste, for instance, or Capella from used in Thales. Then we have to create an ecosystem around. And maybe not an ecosystem around EDS, but an ecosystem, an MBSE ecosystem in which EDS can play a fundamental role.
All right, great. Thanks a lot, David. There's one other question that I think we're going to have to take off into the Slack channel. So if you want to take a look at that momentarily, we'll get that moved over. Excellent presentation and great attendee engagement there. Thanks a lot.